In the next two videos, I'm going to model how to solve logarithmic equations. These should model very closely what we've done with our exponential, so some of the same strategies come into play solving a logarithmic as you do an exponential. We're going to want to make sure that we use our logarithm rules and to help us solve these equations. So first thing, here's a logarithmic equation. It's a natural log base for all of them. But one of the first things we want to think about is, are there any log properties that we can do? We want to condense this. Remember, we practiced condensing and expanding. We want to condense this so that each side is in the simplest logarithmic forms that we can. So what I spot right away is a quotient rule. So I'm going to rewrite this as the natural log of 7x plus 3 divided by x plus 1. And that equals the natural log of 2x. Now that we have a single logarithm statement on each side of the equation, there's a natural log on the left side and a natural log on the right side. What we can do to undo natural logs is to exponentiate both sides to the inverse power, or the inverse base. And natural log is a base e, natural log is a base e, and this is our inverse properties of logarithms, so they reduce or they cancel. So in essence, by using the exponentiation of base e, we've eliminated the logs. So 7x plus 3 all over x plus 1 would have to equal 2x. Now I can get rid of the parentheses since the arguments of the logarithms are gone. So to solve this equation, we're going to multiply both sides times x plus 1. So 7x plus 3 equals 2x times x plus 1. And then we're going to solve this equation. So 7x plus 3 equals 2x squared plus 2x. It's a quadratic equation, so that means we want to get everything to one side and get one side set equal to 0. So 2x squared, moving the 7x over, makes it a negative 5x. Moving the positive 3 over, that makes it a negative 3. And we can try either factoring or quadratic formula, and this one will factor quite easily. So 0 equals 2x, x, plus and minus. I need a negative 5, so I'm going to put a minus 3 there, plus 1 there. Use our zero factor theorem, and we know that x can be either a negative 1/2 or a positive 3. Now the thing with logarithm equations is you always want to check your answers, because you could introduce what is called extraneous solutions. So whenever we're working with logarithms, make sure that you check your solutions. If you don't check your solutions, you might add some solutions in that don't belong in the solution set. So what you're going to look for when you check your solutions is very simple. Our solutions, we said, were negative 1/2 and a positive 3. If I put either one of these values in for x, am I going to create a situation where we take the logarithm of a negative, or in this case, the natural log of a negative? Remember, you cannot take the log of negative numbers. It's out of the domain. So when I plug in this negative 1/2, if I take 7 times a negative 1/2, I get the natural log of a negative 3.5, add it to 3. And this is where I already know that this negative 1/2, cannot be an eligible solution, because negative 3.5 plus 3 is a negative 1/2, which would force us to take the natural log of a negative 1/2, which can't be done. So we throw that solution out. It can't be used. If we put in a 3 times 7 is 21 plus 3, no problem there. 3 plus 1 is no problem. 3 times 2 is no problem. They're both positive. So really, in the end, all we're going to get for a solution on this one is a solution set of 3. So check your solutions to make sure that they're going to work in the original equation, because sometimes you're going to have to get rid of some because they don't work in the logarithm. Okay, second example of this. Again, my goal is to write this as one log statement rather than two. I'm going to utilize log properties to help us do that. So if we see the sum, we know that the sum is the log of the product, so it's going to be the natural log of 2x plus 1 times the 2x minus 3 equals, and I'm going to use the power rule over here, it's going to be the natural log of 2x minus 2 squared. So the first idea, the first key principle is to write it as a single log statement on each side. I have a single log statement here, single log statement there. We'd rather not have any powers lingering in front of our natural log, so that means I use a power rule. Then to get rid of a natural log, we again exponentiate both sides to a base e. That will be our inverse property of logarithms. So what we're left with is a 2x minus 1, plus 1 times a 2x minus 3 equals a 2x minus 2 squared. So now we're going to have to run through some distributive property. 2x times 2x is 4x squared. I've got a negative 6x and a positive 2x. That's a negative 4x. And then we also have a negative 3 equals. When you square a binomial, you get a trinomial. You square the first thing, it's 4x squared. You double the outside inside, so that's negative 4x doubled to negative 8x, and you square the last plus 4. Now we set out to simplify by collecting like terms. What's kind of nice about this one, the quadratic terms drop out when we try to collect, so it will not be a quadratic solution or equation. So add the 8x to 4x, we have 4x. Subtract the 3 from the 4. Sorry, I'm going to need to add it because I did subtract it. So adding it gets it to 7. And then our value is x equals 7/4. Okay, so now make sure you check your solution. Make sure that it does not create a logarithm that cannot be calculated. So 7/4, that's just about 2. So if I take 2 times 7/4 and add 1, that's going to be okay. If I take 2 times 7/4, if I take 2 times 2, that's going to be closer, or 2 times 4, that's going to be closer to 8 plus 3, that's going to be fine. And this one's going to be fine. So it clears that. So our solution set is the set that contains the one value of 7/4. Just a couple of quick examples of those in the next video. Virtually the same idea. They're just showing you in particular more ideas on extraneous solutions.